audience. You guys always are. So now in section 2.7, we're going to talk more about exponential equations. Now, a big thing that we did yesterday when we were solving a logarithmic equation is we exponentiated both sides of the equation. And I made it very dramatic when we did that, really to call attention to the fact that like when you're solving a logarithm, you need to use an exponential. So if we put shoe on the other foot, if we're solving an exponential, what would you expect us to use at some point in the process? A logarithm. When you're solving an equation, usually you're doing a set of like inverse operations, right? Like whether it's a multi-step equation where you need to add something to both sides to cancel out subtraction, or divide both sides to cancel out a multiplication. You do a set of inverse operations in order to solve for your variable wherever it is, okay? However, in last section, our variable oftentimes was inside of a logarithm, right? Like if you look at the one that Ellie and Emmett did, we had a variable inside of a logarithm. We condensed it as much as we could, but still the variable was in there. So how did I undo the logarithm in order to get to the variable? I had to use an exponential. That's what they did. They turned it into an exponential equation, okay? So then at some point, if I'm going to start with an exponential equation, I will likely need to use logarithms to complete that inverse process, okay? All right, so here we go. So first thing, let's do a couple of basic ones, and then we'll move into some of the more exciting stuff, okay? All right, so it says 2 to the t minus 3 equals 8, okay? So I'm going to try to solve these equations by using exponentials. And ideally what I would do is I would get the bases to be the same, and then I would set the exponents equal to each other. So obviously the common base that I want to use is 2, right? Because that's my base on the right side. I can't really make that any more simple. How would I make the left side look like 2 to some power? That's pretty simple. It'd be what? 2 to the third. So 2 to the t minus 3. I have no idea what am I on? Crayon? A green crayon? I don't even know how I got there. Equals 2 to the third power. We're going to write it out though. Okay. Maybe I did this from yesterday. When my bases are the same, what can I do with my exponents?
Make them equal to each other.
I can set them equal to each other. So t minus 3 is then equal to 3. Okay, so I can make them equal to each other. And then I would just solve for t, add 3 to both sides. I get t equals 6. Okay, and if I plug in 6 to check, I would get t to the 6 minus 3, t to the third power is equal to 8. So that all works out nicely. Okay, the one on the right is a little less intuitive. Okay, what would you expect our common base to be for this problem? I would say 3. Okay, now the left side is 9 to the 2t. So how should I rewrite that? Yeah, so 3 squared, but then still to the 2t. So I'll use properties of exponents in a minute to deal with that. How can I rewrite the right side? Right now, I have 3 times 3 to the 1/3. Okay. All right. So we have to rewrite both sides now. We got to simplify both sides. What should I do on the left side? What is that going to look like? 3 to the 4t. So when I have a power raised to a power, I multiply the exponents by each other. Okay, and then on the right side, I have 2 terms multiplied that have the same base but different exponents. What do I do with those? Add them. So it'd be 3 to the what? 4/3. Very good. Okay, my bases are the same. Now I can set the exponents equal to each other. I get 4t equals 4/3. Okay. All right, last step. Divide. What do I get? Cool. Are we all right with that? Okay. All right. Do you guys have your calculators? You need them. If you don't have them, you need them. I have a random one right here. Do you guys have a calculator app on your iPad? You can also use that as well too. Oh man, I didn't take attendance. I didn't do it. They're going to yell at me.
I'm not going to yell at you today.
Okay.
But send it.
All right, got it. I blamed moving the desks as my distraction. Okay. Now, in your calculators, we did a decent amount of work talking about exponentials. I mean, you guys got comfortable with that yesterday. So then today, we're going to work with stuff with logs. Okay? So it says approximate log base 3 of 12 to 4 decimal places. Here's the problem. If you pull up that calculator and you go to put it in, your calculator can only handle 2 types of logs. Which types of logs can your calculator handle? Natural log and then common log, which is log base 10. Yes. So how do I evaluate something that is log base 3? You guys may have learned this in the past. We need a formula for it. But let's get to that formula first, okay? So what I want to do is I want to figure out what log base 3 of 12 is equal to. So let's just say it's equal to x, whatever. That's what I want to find, okay? All right. How can I rewrite this since I don't really have a way to put this in my calculator with log? Let's rewrite it as an exponential, see where that gets us. So if I rewrite it as an exponential, it would be 3 to the power of x equals 12, okay? Now I want to solve for x, but x is up in the exponent. Do we know anything, any sort of math that we can use where we can get something as that's an exponent, like down on the baseline instead? We can do that with logarithms, right? Remember, if you have like log of something raised to a power, you can pull that power in front of the log. Remember that property? So what I can do is we have another property that says if you have, I think we use the letters m and n. So if you have like m equals n, then that's equivalent to log base a of m equals log base a of n. Meaning, if you have 2 things that are equal to each other, you could take log of both sides of that equation, okay? So let's do that here. Which log do you guys want to use? We need to use a log that our calculator can handle. So log base 10. All right, so I'm going to take log of both sides of this equation. So that looks like log of 3 to the x equals log of 12. Was that my door again? No? Was it? Okay. Those darn ditchers. All right, now I can use the property of log to take that x and pull it on the baseline, right? So I can say this is x times log of 3 equals the log of 12. And then I can solve for x by dividing, right? Because log of 3 is just a number. So then I would get that x equals log of 12 over log of 3. So I just divided both sides by log of 3. Okay? Now if I do that, I have arrived at a point where I can put that in my calculator, right? So I can put log of 12 over log of 3 in my calculator. Okay? So when you do that, what do you get? Colin's already got it. What's log of 12 over log of 3? He does not got it.
2.2619.
Okay, that's what you guys said as well too, right? 2.26 something. All right, cool. Now it says how many decimal places? 4. So 2.2619. Okay, is that rounded properly?
Yeah.
Perfect. Okay. I sure hope so too. All right. Now let's do the same thing using natural log. Okay. Now, I'm not going to go through the whole process again, but wouldn't it be very similar, right? Instead of taking log base 10 at this stage, I would just do natural log at that stage. I would still pull the x out in front. I would still divide both sides by natural log of 3. So that would be equal to x equals natural log of 12 over natural log of 3. If I change that log, bless you, will that change my answer? There's only one way to find out. Plug it in and see what you get. What is natural log of 12 divided by natural log of 3? And it's still the same thing, 2.2619, okay? It's because you're taking the ratio of those exponents, okay? And that ratio, though we're changing our logarithm, should remain intact, okay? All right, so that allows us to arrive at what is called the change of base formula. Have you learned this formula before? Have we seen it before? Maybe? Possibly? Okay, well, here's what it says. So if A nor B are equal to 1 and M is a positive real number as well as A and B, then the formula says this. Log base A of M equals log of M over log of A. Or natural log of M over natural log of A. So that is our change of base formula. What that does is that takes a logarithm and it changes it into a base that our calculator can handle. Okay? All right. Now, the way I remember that is the base goes in the basement of the fraction. That's how I remember which way to put each piece. Okay? All right, so that being said, let's approximate log base 5 of 89 to 4 decimal places. Do you guys want to use natural log or log base 10? Natural log. Okay, so log base 5 of 89 equals natural log of 89 over natural log of 5. Calculator warriors, I need you to compute that for me.
2.7889.
Okay. Verified? Yep. Super. Okay, cool. All right, questions there. Change of base. Okay. I don't know where to sit now that the classroom has moved around. I can't sit there because then I'll be in front of Colin. All right, I'm just going to sit here for now. Okay. All right. So let's talk about solving exponential equations in that case. So recall, and we kind of talked about this already, if m equals n, then log base b of m equals log base b of n. Meaning, if I have two things equal to each other, I can take log of both sides of that equation. Okay? So we can use that when we want to solve exponential equations. I can't drive this point home hard enough. If you have an exponential equation, it is likely that you will use a logarithm to solve it. If you have a logarithmic equation, it is likely that you will use an exponential to solve it because those are inverses of each other. They are opposite operations. So I have an exponential equation because, like in the past, I would try to make 14 look like 3 to some power. But do we know what power we'd have to raise 3 to in order for it to equal 14? I have no idea. It's not a nice number. So because of that, I'm going to use a logarithm to solve it. Okay? Now, it is most convenient if you use a common log or natural log, because then we can plug it into our calculator, right? So it doesn't matter. You hate to see it. Sorry, Ethan, I got it. It doesn't matter because you'll get the same answer either one. But you guys tell me, what log do you want to use? Common or natural? Common. All right, fine. I heard them both. We're going to use common. All right, so I would take log of both sides. So log to the 3x equals log of 14. Technically, it would make sense for me to use log of what other base that I didn't even mention? I could also do log base what? Not x, 3. Because then log base 3 of 3 to the x would equal x, right? And then that would cancel everything out nicely. The problem is on the right side, you get log base 3 of 14, so you'd have to do change of base anyway, okay? All right, so my next step is bring x out in front. So x times log of 3 equals log of 14. And then I need to divide both sides by log of 3. Divide both sides by log of 3. And I get x equals log of 14 over log of 3. Now, what I will likely do is I will save I will save plugging my values into my calculator for the very last step because I don't want to round throughout the process, you know what I mean? I want to save the decimals for the very end. Okay, so what would we get if I plug that into my calculator? Help me out. 2.4022. Anybody else get 2.4022? Verified. Cool. Verified. I had a chemistry teacher, Mr. Sample. He's one of the best teachers I've ever had in my life. And anytime we had a calculator problem, that's what he would say. So he would ask for an answer, someone would give an answer, and then he'd say verified, And then someone else would have to like give a thumbs up that they plugged it in and got the same thing. So that is an ode to Terry Sample. All right, so 5 times 2 to the 3x equals 8. See, it wasn't even a math teacher that made me want to be a teacher. It was Mr. Sample. Which is an incredible name for a chemistry teacher, honestly. Okay. What should we do first?
Divide both sides by 5.
Yes. Please don't multiply the 5 and the 2. You can't. Why not?
Because they don't have the same base. Or they're not both exponents that are the same base.
Yeah, so they don't have the same exponent, really. If they had the same exponent, then there is something you could do to interact between them. But because 2 has the exponent of 3x, I cannot multiply the 5 and the 2 by each other. So that means I need to divide both sides by 5 first. So I would get 2 to the 3x equals 8/5. It's a weird looking 8. All right, now what do you want to do? Log. Natural log, common log.
No, we should do log base 2.
You want to do log base 2, right? I wouldn't do log base 2 for this one. I should have done it for the last one, but let's do common log. So log of 2 to the 3x equals log of 8/5. All right. Now I need to bring my exponent out in front. So 3x times log of 2 equals log of 8/5. Now I need to divide. What am I going to divide both sides by?
Log 2, 3 log 2.
I would do 3 times log 2, right? Might as well get that out of the way as well, too. All right, so then x is going to equal log of 8/5 divided by 3 times log of 2. All right, plug that into your calculators and tell me what you get. That's a bit of a convoluted process to plug in. Probably. What'd you get? 0 point something. 0.02?
That doesn't sound right.
0.05? You're getting doubted already. Ethan's not verifying it. What'd you get, Andy? 0.2260. 0.2260?
Verified.
Yeah.
So that's verified.
I'm trying to think about how you would have arrived at your value, Ella, or Ellie. What'd you say? It's because you used Emmett's?
Yes.
Emmett, what's wrong with your calculator? All right. It should be 0.2260. If you can't find your mistake, let me know and I'll help you out after class. Okay. Okay, we got 2 left and we have 3 minutes. Here we go. Okay, we'll do the word problem and then I'll try to do example 6 and then you guys will walk out the door as the bell's ringing. Okay, so in 1990, there were about 5.4 billion people in the world. If the population has been growing at 1.95% per year, estimate the year when the population will be 8 billion. What formula should we use? Bless you. What formula should I use here?
Continuous growth.
Okay, so what's that look like? A equals P. I'm not going to use PERT. I'm just going to do 1 plus R to the power of T.
Oh, yeah, I guess.
Yeah, we got to use our exponential model here. Okay. All right, so where am I going to plug things in? 5.4, where's that go? P. What about 1.95? So 0.0195?
Yeah.
You guys cool with that? I don't know T. That's what I'm solving for, right? How long? What is my A value? 8. Good. All right. So, what do I want to do first?
Divide by 5.4 billion.
Yeah. I'm just going to leave it as 5.4, and we're going to get our answer in billions. So we'll do 8 divided by 5.4, so whatever that is, equals, and then in parentheses, 1.0195 to the power of T. Woof. What should I do to both sides? Log it. So log of 8 over 5.4 equals log of 1.0195 to the power of t. And then the process is the same. The numbers are just more difficult. You got one left in there, Charlie. Good Lord, man. Is it the logs that you're allergic to? Allergies are bad this time of year. All right, so log of 8 over 5.4 equals t times log of 1.0195. Okay. My last step is division. It's log of 8 over 5.4 poop. All right. This last one you'd have to factor like a quadratic and then just set both equal to 0. Okay? Your homework is here. Complete that for tomorrow, and then we'll start reviewing.
It's a little bit of a conservative estimate.
Have a great day and go Minutemen. You said what?
Go Guards.
Problem's a little bit of a
Go.
conservative estimate.
Yeah. Right.
We're already at